Hello, everybody. Welcome to this session about a crazy thing that you can or maybe want to do with your application, which is running them in parallel on two clouds. Whatever the reasons are. Who am I? I am currently a cloud architect at Zencor, a company that is a partner of Google Cloud. So we tend to engineer clouds on Google Cloud and run people's applications on them, or help other companies build whatever idea, whatever need they have on Google Cloud. And our customers tend to be on other clouds before they come to Google Cloud, sometimes, unless they are a startup. So we do these things, and this talk is actually based on a project that I am currently finishing. Little warning, I have a cough, so I might start coughing during the talk. I apologize for that. I have tea, so we are prepared. My background is in DevOps and systems and clouds and all sorts of infra, and I'm also a Google Developer Expert, which is a recognized kind of ambassador community, and also a photographer. The QR code leads to my social media if you want to stay in touch. I will begin with this wonderful slide, which shows two nearly identical graphs. This is a Grafana dashboard for request count per minute on an app called Content API. And we can see that one points to AWS and the other one points to GCP. This is a 50-50 traffic graph between AWS and GCP, Content API. Content API, as you might want to guess, is an app that serves content via an API. Surprise. How exciting is that? Here's where I would typically go into the problem statement and delve into the reasons why and what are we trying to solve, but I will not do that because all of you have read the talk description, and this is an absolutely bonkers, ridiculous, and most expensive way to run your applications. So we shall not talk about the reasons why and dive into how. What do you need to understand about your application before you can start attempting to run it on two clouds at the same time? The first thing you need to understand is the deployment patterns. I will say immediately that you need Kubernetes. You need your applications to be architected into a microservices pattern that can be decoupled one from another, that can be continuously deployed, and you have an abstraction layer that allows you to change parameters such as the artifact registry addresses, the cluster addresses, and so on. In this particular project, we were using Flux and Customize and just pushing images into two different repos. And so having a well-architected and a well-decoupled architecture with like an event stream in between caches and all of that allowed us to then think about the second thing you need to think of, which is the dependencies between your services and the relationships between your services. What do I mean by that? Ideally, in an ideal scenario, you will have part of your product that is going to be reading data from databases, buckets, topics, whatnot, and a different part of your product that is going to be writing that data. If you have that decoupling, it makes it really easy to then separate the traffic and figure out what goes where, and also deploy the applications in two different clouds, two different infrastructures in parallel. Because guess what? When you have apps that write, how are you then dealing with data consistency? If you are running the same application in the same region, in the same environment, in two places, and it writes data into two different databases, or maybe it writes data into the same database, but how is it aware of the other side? You're dealing with a lot more complexity. So ideally, you will have a part of the app that is read-only and the part of the app that creates data. This was the case for this project. The platform contained some sort of 300 microservices, maybe a bit less, but they could all be easily placed either into content serving or into CRUD, so data writing, data creating apps, or into data analytics. So you could figure out what to do with them. I mentioned data analytics and databases and streams and buckets. What do you do with your data is a huge part of figuring out how to run your app on two clouds or to any infras, right? Data consistency, data quality, replication. How do you figure out where to store that data? Is it on one cloud and then you're paying all of the data transfer fees? Is it on both clouds and you're paying double? What are you doing? And DNS. And I'm going to leave the DNS to the very end, because it is quite clever and quite simple, and actually the key into doing this thing. Let's start with little details of what you need to think and what will likely be different within those 4 big points that I mentioned. The application deployment patterns. I mentioned that you likely want to have a CI/CD tool that is fully abstracted and fully coded and customized, FlexCD or Argo or some sort of thing that manages your Kubernetes deployments. Most of the things, if you do have a CD tool like Flux, you will be able to just redeploy the same manifests. You know, the concept of Kubernetes is that whatever it is Kubernetes. And you can just take your manifests and deploy them on the other side. There will be some differences, though. For example, between EKS and GKE, on EKS, you have to deploy your own Prometheus and Fluentbit and all of the observability and log management tools. On GCP, they are managed. Is that going to fit for you? There are limitations. There are things that you cannot do with fully managed Prometheus and fully managed log collectors. The other thing that is different is secret management. And if you use any sort of encryption keys, you will have to adapt those parts. Secret management, hopefully you're using something like external secrets, which will allow you to just point it to a different secret store. Good days. And ingresses. Again, taking the example of EKS versus GKE, on EKS you will use the ingress controllers. On GKE, you can use GKE Gateway, which is the adaptation of the Kubernetes Gateway API, which is the way forward for ingress management in Kubernetes and any sort of service-to-service or external-to-service communication. Within Kubernetes, the community is slowly moving towards the Gateway API being the central point. And it's very well adapted in GCP on GKE, so you can use GKE Gateway, but that changes how you deploy your ingresses and how you manage your DNS as well. And one very, very important thing, the project that I am talking about got delayed by 3-4 months because the team was not happy with the observability that they had. And then when we finally started deploying to 2 clouds, it turned out that they were totally right to do that. They took their time to build the dashboards. They took their time to figure out the exact detailed point-to-point observability that they needed for their apps. Luckily, they knew their application stack really well. And all of the screenshots that I'm going to have about the app deployment process were from the dashboards, and they're beautiful. You need good observability. If you have something and you're happy with it now, once you increase your complexity, you will need that much more. So pay attention to that and spend the time. Don't be afraid to spend the time on observability. Between inter-service relationships and behavior, I kind of described it already. Ideally, you will have a decoupling between your services and between your applications that you can analyze and deploy accordingly. So in this ideal scenario, which we conveniently had in the project, was that we decided to deploy a dual cloud run of the content serving part, and then the part of the platform that does content creation and data writing, that one only runs on one cloud. So you can adopt a strategy like that. For whatever reason you're trying to do this. We were trying to migrate from AWS to GCP, right? And at some point in time, there was a period where the app was running on 2 clouds at the same time. But if you're doing this for resiliency, let's say you have a regulatory requirement that says that you need to be prepared for the event of AWS disappearing, we will have much bigger problems if AWS or GCP or Azure disappears from the face of Earth, but you need to be prepared. If you want to be prepared for that, you might want to have a way to switch the DNS of your data writing part over to the other cloud, but while it's not there, it's just sitting there, not doing anything, with 1 or 0 replicas or something like that. There are strategies that you can deal with. There are strategies with the data if you do want to run on 2 clouds fully. For example, if you have a customer that wants your app to be on a particular cloud provider and they are consuming your service, there are strategies to do that, but it gets more complicated when you have to deal with data consistency. What was the migration plan in general for us? This was, like I said, a migration project fully. So we were first setting up the infra, then migrating the content-serving apps, which included the dual cloud run. Then we flipped the apps that write data. Last night, we finished at 10:30 p.m. And data analytics pipelines was a long and dwelling process because for that one, if you are dealing with analytics pipelines, you'll need to remember that maybe they are not idempotent. Maybe your pipelines don't know how to deal with duplicate data. And that obviously requires testing on some sort of subset of data. And then finally, DNS migration. DNS migration in this project hasn't happened yet, a full DNS migration from AWS to GCP. But if you're running in 2 clouds at the same time, you don't really need to migrate DNS from one provider to the other. You pick one and stay there and manage everything there. So how does it look like if you want to run on 2 clouds? It looks something like this. I'm not going to dive into the details of each of the steps. There will be a QR code at the end where you can access the slides. Now let's look into the data, because this is where it was exciting. Okay, you copy 1,000 Flux manifests and customize manifests. Cool. You've done a lot of YAML writing. But data is exciting. How do you deal with that? The strategy is, to have a bidirectional replication of data. If you are doing 2 places at the same time, you will want to make sure that each of them has the latest and greatest of the data. Little pause for tea while that point sinks in, because it is the most important one. We wanted to use managed services instead of in-house to simplify things. Can I write a script that will do an rsync from one bucket to the other? Yeah. Do I want to? No. Cloud native where possible to make our lives easier. Data integrity preservation is a big, big, big point, which is why we want to use managed services and not write our own. And we want near real time. And I'm going to get into that because it's not always possible in every cloud provider. But we want near real time. The services that make it possible, the products that make it possible for databases, we wanted Postgres, we were using Postgres. It's possible with Postgres. RDS and AlloyDB. AlloyDB is a cloud-native Postgres solution on GCP. Object Store, very obviously S3 and GCS. Event streaming, MSK, Kafka, managed Kafka on AWS, and on GKE we were running StreamZ Kafka, because managed Kafka on GCP wasn't available when we started. Now we would do managed Kafka on GCP, and we actually did it for a different project. Works really well. But first, before we do these things, we need to make our 2 clouds talk to each other, right? We need to connect them. We need to figure out how the data will travel over the internet. Now, it depends also on your case whether or not you need everything encrypted, or maybe you just want to protect your data nicely. So we need a VPN or an interconnect, but interconnect is an overkill in most cases. So VPN. We connect each AWS VPC to a GCP VPC. That is one of the big differences between AWS and GCP. Your VPCs on Google Cloud are global, and then you have subnets per region. On AWS, you have separate VPCs per region. You connect them with VPN gateways, make them talk to each other, and then your Kafka and your databases will send their data over the VPN. But not buckets. Buckets will travel over the internet. That's just easier. You can make buckets talk over the VPN as well. Requires a bunch of setup. It's going to be expensive. because you have to pay for the VPN. And it's not really that necessary. The tools that replicate data between AWS and GCP in the object stores, they will do the encapsulation for you. Place here. For Postgres, you use something called pglogical, an extension, which you can install on instances of RDS and instances of LODB. What happens here is in each database, you'll have a node and a subscription, a node that represents the other side. I apologize. The node represents the other side, the subscription represents the copying of the data. This is a bit painful. You'll have to do this for every single database that you have. But then it works. And this is real time. So as soon as the data lands in one database, it's copied over to the other database. You need to provision enough space and capacity in each database to handle the load of replication. For object store, we're going to use cloud-native tools. And for Google Cloud, we use a storage transfer job, which copies data from S3 to GCS. And when I started doing this, I thought, well, surely it handles bidirectional replication. Would be logical, but it doesn't. OK, what do we do? Write our own pod that will copy data? Nah, don't want to do that. Surely AWS has something like that, right? Data sync. OK, cool, data sync. Storage transfer jobs can be event-driven. You create a bucket notification on AWS, send it to SQS. The transfer job will pick it up, copy the data over as soon as the object lands. Good news. Data sync, you need to build a nuclear power plant for it to run a job. And it can't run too many jobs in parallel, because it's sensitive. And it can also not run it event-driven or in real time. It can only run every hour. And it also cannot look at the bucket and have a notion of what it has already copied. It has to analyze every single object, object by object, every single time it runs. The poor little thing. A job that would take, I don't know, a backfill job for 300 gig from S3 to GCS took like 20 minutes. Data sync jobs take an hour every time, because they look at that bucket and they go, do I know this object? Yeah, I know this object. Do I know this object? Yeah, I know this object. Please. You can terraform all of this, obviously, but this causes a problem. The fact that this is not data-driven causes an issue. Because guess what? If you were running your data writing apps, the CRUD apps on GCP, and you have 1 hour delay before it gets to AWS, that's not cool. So in this case, the data writing apps stayed on AWS until we migrated everything. I'm going to do a demo. Hopefully it works. We have some Terraform that I'm going to show you. Terraform that sets up the data sync and sets up the GCS stuff. So if I look here, is that big enough? Like that? Better? Great. OK, we have a module for data sync and a module for data transfer jobs. In the main, we have I created a bucket on either side, and we set up the storage transfers and the data sync. I'm going to kick off a deployment first and explain, while it deploys, I'll explain what's going on. Meanwhile, this is the bucket that I have on Google Cloud. We have a bunch of screenshots from the Devoxx UK website. And we have a bucket on the AWS side, which has a couple of GIFs. And the UI is marvelous. OK, we have a couple of GIFs. Cool. We see that the objects on either side are different. That was the point of showing it. Let's deploy the data sync first, shall we? So I'm going to run, I don't need an init. I think I just need an apply, and I'm going to do a target because I want to show you the difference. While it is doing its thing, I've been warned that the internet is not fantastic here, but it's OK. We're going to make it. 17 objects, 17 things that we need to create for the data sync. This is the nuclear power plant that I was talking about. For a single job, we need to create 17 resources. You need an instance, you need a VPC endpoint, you need a connection, you need security groups left, right, and center, IAM roles, a lot of things. OK, let's go. In the meantime, while this is doing its thing, let's see what's in the data sync module. So we have CloudWatch, because we need to monitor. We have the data sync agent, which is, let's look into that. So we have an instance. We need to deploy an instance for data sync. Serverless data transfers from anywhere to S3. Now you need an instance. So we have the instance. And then the agent. The agent will connect the instance to data sync service. What else do we have? We have the tasks. The task will be the actual job with configurations like how do you override, what's the transfer mode, what's the validation mode, and of course, the locations. Here, you don't specify just, bucket 1, bucket 2. You need to first create the locations, the source and the target and the source in this case. And that would be in data sync locations. So target S3, source. For each source bucket, you need to create a data sync source. And then you connect all of them together in a task. Sorry. This is still creating. The other important thing about this, all of this is IAM, of course. You need to allow data sync to read from the source buckets. You can do that via a storage key of a service account on Google side. So if we look into IAM, we can see, well, first of all, the instance stuff, roles, policies, blah, blah. And then for the data sync itself, you allow it to read from the buckets, and then CloudWatch to write logs, because you want logs of what worked and what didn't work. Where is the key? Somewhere here. You provide it with an HMAC key and the Google service account. Here, you create a service account on the Google side, and then you give it access to the bucket that it needs to read from, and then you create a storage key, special key. And you need to do kind of the same for the other direction as well, right? So you will actually fetch the identity of the storage transfer service account, service agent, on Google side, and then create a federated IAM role on AWS side. We have now applied. Let's go and have a look in the data sync itself. We will now have a task. We have the locations, which will be one is the source and one is the target S3, and then in the tasks. These tasks, you can run them on a schedule, again, a minimum of 1 hour, or you can start them manually. And so I'm going to start it. It's going to take its time to initialize and execute. In the meantime, I'm going to apply the storage transfer side, so the Google side of the bidirectional replication. Well, I don't remember what the module is called, so I'm going to do this. The task is running. We see the information about the task, and we can monitor eventually when it's run. So it's still launching. It takes its time. The launching stage will figure out the task and then analyze the source data, which in our case, again, is a couple of images that we want to copy. Cool. I'm just going to say yes. We see that there are 10 resources to add. And we have 2 jobs. And I'm going to explain in a second why we have 2 data transfer jobs. 10 for 2 jobs instead of 17 for 1 job. Again, why do we have to do such a complicated thing? Oh, well. Why do we need 2 jobs? If I go into my definition, we will see that there are 2 jobs. First, you need a backfill, because we are doing event-driven data transfers, right? So as soon as a new object arrives, we will copy it over. That doesn't tell data transfer about the fact that there is existing data that you want to backfill into your GCP. So for that case, for that reason, we will create a manual job first, backfill, and then the event-driven one will copy over every new object that we have. What is in the module of the data transfers? Well, we have IAM. Again, I mentioned it's the access to the S3 buckets, it's the access to SQS queues. We have the bucket notifications. I configured it like that so that you can just point it to an S3 bucket and it will set up everything that is needed for the event-driven. But obviously, if you already have bucket notifications configured on your S3 buckets or on your GCS buckets to go somewhere, you will have to add a new target, a new SQS queue for data transfer, because otherwise they will go into a conflict. Variables output, and what's interesting is the transfer jobs. There's a couple of abstractions that I've done just because it's a module. We want logging, again, of course. We don't need to allow it to do logging, but we do need to configure the logging. And another interesting thing, we will exclude AWS datasync. Datasync creates a folder inside the S3 bucket into which it puts its metadata. We don't want to copy that over. That's not actual data. So we're going to exclude it by default. And then you can configure some of the other things. Like datasync, like S3, like the data transfer jobs, they all have different sources that they can copy from. But of course, for this particular instance, I was interested in doing bidirectional between S3 and GCS. So this is what it's pre-coded for. Oh no, a resource already exists. I thought I deleted it. Well, turns out I didn't. OK. Or maybe I can't. Let's go and have a look. I obviously tested the demo before doing it. Interesting. I think I'm going to need to rename this wonderful thing. Right? What are we doing here? We're creating the jobs. And they do not exist, as a matter of fact, but Terraform thinks that they do. But if I rename the jobs, it's going to rename the datasync resources. So I'm going to show you what datasync did before renaming the resources. OK, so datasync succeeded. It transferred 4 files. It gives you the data about how and how fast, and so on. And so now if we go into the target bucket, we're going to see that the DevOps images are here. And we can see them. So I'm going to rename the transfers. The reason why this happened is because I had tested the demo yesterday and created the jobs and then deleted them. In GCP, not every single resource is going to be deletable immediately, especially when it comes to data. There is a 7-day to a 30-day safety period where you can recover your data or you can recover your resources. So I believe this is what's happening here for storage transfer jobs. If you deleted them, maybe you want to bring them back. And so for a certain period of time, you can't create another job that is called exactly the same as this job. So I don't know. DevOps. Okay. The same thing applies to project IDs and bucket IDs. For example, the project IDs and bucket IDs have to be unique across the entirety of Google Cloud. Same for S3 buckets, they have to be unique across the entirety of AWS. And if you, let's say, delete something, if you delete a project, you have 30 days to restore the project. So I once deleted prod US. And clicked restore within 2 minutes, so all of the data was still there, luckily. But it also means that you can't create a new project with the same ID immediately after destroying an existing one. You'll have to use a new ID. This creates all of the debate around, oh, should we add random characters to the project IDs? I'm not a fan of that. I like to know where I'm going and to not have to look up the random IDs of the projects every single time, but hey, it's safety precautions. Oh yeah, this is gonna recreate the bucket notifications and stuff like that. So when you are doing this potentially with production data, right? There is a couple of defaults that I decided to set, which might be interesting to see while it's doing its thing. The default, for example, for delete objects from source after transfer. False. Please don't delete my objects. What this would do, if you are doing just a transfer of data, you might want to delete the objects that have been transferred already, right, from the source. But because we're doing bidirectional, we still need the data on either side. So please don't. Overwrite when it's different. This is an interesting and a bit of a tricky one. Again, when do you override an object that you have already copied, or maybe that has been created by a different entity on the other side? Override it when different. Again, we want data on either side to be exactly the same and to be as consistent as possible and as fast as possible. And things like if you need to transfer only a subset of prefixes, you can configure that, obviously. The only thing that is maybe trickier to do when you're setting this particular thing up is if you have source/target buckets in different AWS accounts. Because then with AWS, you need to initialize Terraform with a specific account, specific region. So if you're doing multiple different accounts, then you will have to have different providers. How do you deal with modules? It's not as simple and elegant as I'm showing here with just a Terraform that calls 2 modules and will magically create everything for you. It will be a bit more difficult. OK, cool. We have succeeded. What do we have now? We were looking at transfer jobs, and there was like an old one, but now we have the DevOps ones. OK, the event-driven is already in progress. It starts immediately. But I said that we need a backfill, so let me make this bigger. So let's start a run of a backfill job. Again, this will look into the S3 bucket and just copy over all of the data that doesn't already exist in the GCS bucket. ta-ding, we have the GIFs. You saw that it was really fast, a lot faster than the data sync job. Because it's truly serverless, there's no instance to wake up, and it works somehow much faster in comparing the buckets. Even if you have terabytes of, well, if you have terabytes of data, it's probably going to take longer than 20 minutes. But if you have like half a terabyte of data, it will still run relatively quickly compared to data sync. So again, considerations. Where are you running? Where can your applications function the way they need to function? Do you care about the delay? Is it OK to wait for an hour before the data appears on the other side, and so on? Now, this was a manual backfill. We still have the job that is event-driven. So let's upload something to the bucket, to the S3 bucket. I have a GIF, another GIF that I'm going to upload. And hopefully, yeah, internet is fine. Perfect. OK. So 3, 2, 1. I have a timer here in seconds. It said 13 minutes, 25 seconds when it uploaded. Let's see how long it takes for the GIF to appear on this side. And it's already here. So it took less than 10 seconds for the 7.5 meg file to appear on the other side, given that the bucket needs to send a notification to SQSQ, and the job needs to pick it up and needs to copy the data over. And you have 2 Ukrainians sending you a heart. The guy is Vadim Pinchuk. He's a Flutter speaker based in London as well. So this is how this works. I'm not going to demo Postgres because that takes a very long time to set up. Again, you need to set up all of the nodes and subscriptions and stuff like that. For Kafka, you use Mirror Maker, deployed into a Kubernetes cluster, connected to both clusters, job done. Well, configure it, of course, job done. You do, again, need really good monitoring for Kafka. So something like K-Minion would be good, or something like Lenses to monitor what's going on and what's going on with your Mirror Maker as well. The offsets, the drainage, the delays. But it's relatively simple. And Mirror Maker 2 supports bidirectional replication. So that's good as well. Now, what have we not spoken about? We have not spoken about DNS. How do we do DNS? First of all, we have the problem of having multiple regions. If you have a problem of having multiple regions, let's say you have the main domain and you need to serve multiple locations in which you have deployments. But now we also add 2 clouds in its deployment. How do we deal with that? The answer is DNS load balancing. For the latency-based, for the different regions, you do a latency-based DNS load balancing where you have your main domain and then CNAMEs that will eventually point to something else. And then you do latency-based load balancing. Wherever the request is coming from, it will go to the nearest DNS endpoint. And then you add A records, or this is actually a CNAME, but doesn't matter, A or CNAME records that point to your ingresses on each cluster. So in AWS, we have external DNS managing the ingress objects. On GCP, there's an IP address because it's a gateway API, so one single load balancer entry point to each cluster. So we know the IP addresses, and we can point to them. And you do weight-based, 50-50 over the 2. Well, you, of course, don't do 50-50 first thing first, immediately, but you eventually get to 50-50. This is kind of what it will eventually look like with the infra on either side. But what happened when we actually did it? I'm saying you wouldn't do 50-50 immediately. So what did we do and how did it go? Before the migration, the stats looked like this. You have AWS with all of the requests across 4 regions. And then on GCP, you just have the health checks. So it's a very regular pattern because every 2 or 5 minutes there is a health check. And then we changed to 99% on AWS and 1% on GCP because we didn't know yet if it's going to work at all. And you can see that the CNAME points to Kubernetes ingress on Amazon and then just an A record for GCP. We did region by region. Southeast Asia, no, South America. Yeah. Observed that it took effect, and then observed the traffic going up. Everybody was so happy, and it was really funny across the weeks to watch everybody's reaction. Like, this is 1% of traffic, and we were watching it so closely on every dashboard that exists. We're watching it in log analytics. We're querying the logs. We're querying everything. Very, very scrupulous for what? 1 request per second? And then when we got into 50-50, like, okay, Asia, fine. South America, fine. Europe, fine. Like, 20 minutes, we're done. This is what it looked like when we did 99 AWS, 1% GCP for all regions. So we could see that there's about 1,500 requests per second and about 15 requests per second. So the distribution looked correct, and we were also watching it in all of the other things. Then we did 10%, and that's where the CTO was like, "Whoa, this looks like a SpaceX liftoff," and everyone laughed, being like, "Well, which one? Are we talking about the one that will eventually crash and disassemble? But let's hope not." And then eventually we did 50-50. The same way, changing the weights on AWS. So the DNS stays on AWS for 53. And we could see that the traffic eventually on all of the different APIs and content functions and stuff like that went from however much it was to then balancing on 50-50 on 2 clouds. And then we watched it. Because there are spikes, right? There are 1,500 requests per second is like considerable amount of traffic, and there are spikes sometimes. How are we going to scale? Fine. Is our latency okay? Because it's a different region. When you're choosing regions, that's interesting as well, because, for example, on AWS, Europe West 1 is Ireland. On GCP, that's Belgium. But did it actually go well? Was it actually running fine? And that was an interesting observation, because we were watching so scrupulously every single request. We noticed that there are things happening. One of them was a load of 429s, and this is Logs Explorer on GCP, and we could find loads of 429s that ended up being a rate limiter between services. And then we zoomed into the success rate, which looked linear, and found that it's not linear. It's not 100%. And on AWS, it was kind of 100%. And then we started diving into what's going on. And there were a couple of very interesting things that came up out of that. First of all, this success rate and these errors. So there were 502s and 503s. There is a documented situation where your GKE gateway, so your gateway API and your load balancer will throw 502s, 503s if your pod dies and the NEG, the network endpoint group that sits between the load balancer and the pod, doesn't know yet. And so the load balancer is still sending requests to the pod that has already died, or is shutting down, or is out of memory. To deal with that, you use a pre-stop hook in the pod configuration, and you can also use things like graceful delays on the network endpoint group. And we found out that the base image for the apps didn't have a sleep library. So the pre-stop hook that they had configured didn't work because there was no sleep library. So on AWS, it didn't work either. It just never worked. They never had a working functional pre-stop hook. Nobody just looked into it with such attention ever. So we fixed that. But why were pods dying anyway and scaling up? And then we noticed that, okay, let's just give them more CPU. Okay, it's looking better. Is GCP CPU not as powerful as AWS CPU? What's going on? Why are our services needing twice or sometimes 4 times more CPUs on GCP compared to AWS? Weird. Turns out, on AWS, they were running on a very sexy, very modern, very nice compute-optimized machine type. And we just hadn't looked into that before. Nobody noticed. And so then we changed from E2 on GKE, which is like a regular, normal, whatever machine type, maybe like an M4 or M5. We changed to C2D, which is a compute optimized with a very modern silicon chip. And immediately, all of the errors went away. And immediately, the latency went down. And we no longer were seeing these fluctuations in the success rate. And we also could bring down the number of CPUs required for each service. And it turned out to be even slightly better than on AWS. That was a really cool observation. You always hear these, I think AWS Summit announced the newest Graviton chip, which is 40% faster than all of the other chips. And you're like, yeah, sure, marketing. And then you actually watch a content-serving app struggle and throw errors left, right, and center because the chip wasn't as powerful as on the other side. That was interesting to see in real time, the actual difference that it makes. And then we had a happy, steady 50-50. And we stayed there for a while to make sure that it is actually 50-50. So the apps were running, the customers were happy, latency was good. We fixed a bunch of issues that existed in the app, but nobody has ever noticed. That was really cool. That's all from me. You can stay in touch here with this QR code, or you can download the slides or access the slides through this QR code. Thank you very much.